8.1 Matrix Algebra. So in the book, it uses matrix with the parentheses, but I don't like that. I usually use the bracket like this as a matrix. You will see all of the problems that we have. We're going to use this bracket. The matrix is row by column. So when we say the dimension, this is row 1 by n because the last number is n. And this is total n by 1. So this is row and the column. For the addition, you just need to take the element for each matrix and then add or subtract. Matrix 1, 2, 3, 4 minus 5, 6, 7, 8. Then this is 2 by 2. This is 2 by 2, meaning 2 rows and 2 columns. And for the addition and subtraction, you just need to take the same location and add or subtract. So the result of this guy is going to be
1 minus 5 for first row, first column, 2 minus 6, first row, second column, and second row, first column, 3 minus 7, and finally 4 minus 8. That's going to be the answer.
Addition and subtraction, we have to have the same dimension. Otherwise, we cannot add or subtract. So that means if we have 1, 2, 3, 4, and plus 5, 6, 7, 8, 9, 10, the first one is 2 by 2. The second one is 2 by 3. Since they are not the same dimension, we cannot add or subtract. That makes sense. The first one minus 5, the second 2 minus 6. So there's nothing we can do about the third column, so we cannot do that. So addition, subtraction, we have to be the same dimension. But the multiplication is completely different. So for the multiplications, we need to multiply row by column. Here's what we're going to do. So we're going to multiply A times B and row by column. Going to multiply that. So before we actually do this, you need to identify the dimension of the matrix first, so which is 2 by 2 and 2 by 2. When we do multiplication, the inner number, they have to be the same. The outer numbers is going to be the result. This the first one is 3 by 2. Second one is 2 by 2. Again, the inner number is the same, so we can multiply, and then result is going to be outer number. Let's do this. 4 times 9 plus 7 times 6. That's the first column, first row. Okay, so we're going to use first row and then first column. We multiply that here. And then first row and the second column is going to go in here. 4 times -2 plus 7 times 8. Second row, first column, 3 times 9 plus 5 times 6. And then second row, second column, 3 times -2 plus 5 times 8. The part B, inner number match up 2 and 2, outer number is 3 and 2. So the result is going to be 3 by 2, A times B.
First row, first column is going to be here. 5 times -4 plus 8 times 2. And first row, second column is going to be first row, second column right there. 5 times -3 plus 8 times 0. Second row, first column is going to be here. 1 times -4 plus 0 times 2. Second row, second column will be here. 1 times -3 plus 0 times 0. Third row, first column is here. 2 times -4 plus 7 times 2. Third row, second column gonna be here. 2 times -3 plus 7 times 0.
So we need to multiply any scalar from here. Let's say 5 times A. That means we need to multiply 5 to every element inside of that matrix. 20, 35, 15, 25. Another important one is the transpose matrix. So let's say
A is 1, 2, 3, 4, 5, and 6.
What's the dimension of this matrix? Row by column. So 2 by 3. A12 equals, meaning the first row, second column, which is 2. A22, second row, second column, which is 5. A23, second row, third column, which is 6. So you need to know this notation so that you can answer it properly for quiz 1. And if you multiply scalar to A, let's say 2 times A, 2, 4, 6, 8, 10, 12, we need to multiply 2 for every element. Now, when we have transpose matrix, okay, we're going to switch row to column. So the matrix A, the dimension of the matrix A, 2 by 3. That means transpose matrix is going to be 3 by 2, row to column. So 1, 2, 3, 4, 5, 6. And there are some special matrices. If there are all entries, all elements are zeros, zero matrix. I want you to know identity matrix. And this identity matrix is the capital I and has to be the square matrix. So 2 by 2, 3 by 3, or 4 by 4. The diagonal one is 1 and all others is going to be 0. We'll use this identity matrix later sections. System of linear equations. This is going to be one important one for our class. What we're going to do, we're going to learn Gaussian elimination method, Gauss-Jordan method. Those are the two different methods that we're going to learn. So Gaussian elimination method is just part of Gauss-Jordan method. We need to put this into matrix form first.
Take the coefficient from each equation: 2, 6, 1, 1, 2, -1, 5, 7, -4. And then we're going to use line bar and put 7, -1, 9.
Our objective is to go from here to 1, 0, 0, 0, 1, 0, 0, 0, 1 bar A, B, C. The left side of the matrix, we saw this, right? What we call this? Identity matrix. This is the coefficients of the x1. This is the coefficient of x2. This is the coefficient of x3. That's what we started. So the first equation, 2, 6, 1. Coefficient of x1, x2, and x3. Second equation, 1, 2, -1. So once you get into this identity matrix for the left side, and then we have some number A, B, and C on the right hand side, then at the end we can say x1 equals to A, x2 equals to B, x3 equals to C. We have to do this using very systematic approach. And step number 1, first row, first column, make it 1. Easiest way, divide the whole row by whatever the number. So by looking at in here, in our first row, is a 2. So if we divide everything by 2, 1, 3, 1 over 2, 7 over 2. This is perfectly fine. So that we have 1 right there, right? Or can switch rows. If I switch these two rows,
1, 2, -1, -1, 2, 6, 1, 7, 5, 7, -4, 9. Now I have 1 right there.
so if there is no 1 in the first column, I said first column, you don't see any 1 in the first column. You have only option to divide by that number, first row, first column number, so that we can make it first row, first column as 1. But if there is 1 somewhere, you can switch them. Why switching the rows is better? Because looking at here, we have a fractions. Later, we end up possibly getting some fractions, but we don't want to have a fraction from the beginning. It's going to be, a little bit of extra work. So I'm going to keep this. So we want to do this. And then step number 2, once you make 1, all below numbers to be 0. So this guy, we need to make 0. This guy, we need to make it 0. How? Using first row. This is important. We have to use only first row to make the bottom rows, first column 0. So I'm going to use first row. So R1 times -2 plus R2, put it back to R2. So we have to use first row always. If we do
-2, -4, +2, +2, and then R2, 2, 6, 1, 7, and then add 0, 2, 3, 9.
Now we have
1, 2, -1, -1, 0, 2, 3, 9.
And similarly, to make the 5 to be 0, we need to do R1 times -5 plus R3, put it back to R3. Again, we have to use R1.
-5, -10, +5, +5, R3, 5, 7, -4, 9. We add 0, -3, 1, 14.
Okay, step number 3. I should say element. This one, element 1, 1. Element 2, 2 to be 1. So where is the element 2, 2? This guy. So for this time, we have 0, 1, 3 over 2, 9 over 2. No other choice but divide every row by 2. And then we're going to make element 1, 2 and element 3, 2, they equals to 0. So this portion, right? Those two elements, we need to make that 0. Again, using row 2. We use R2 times -2 plus R1. Put it back to R1.
0, -2, -3, -9, and R1, 1, 2, -1, -1, and then add 1, 0, -4, -10, 1, 0, -4, -10.
Then R2 times 3 plus R3, put it back to R3.
0, 3, 9 over 2, 27 over 2, and then row 3, 0, -3, 1, and 14. We add 0, 0, 11 over 2, man, big number, 28 over 2, right? So you add 55 over 2, 0, 0, 11 over 2, 55 over 2.
Step number 5, E33 now. We want to make it to 1. We're going to multiply 2 and then times 1 over 11, 0, 0, 1, 5. So by doing this, we already have E33 as a 1. Now step number 6, E13 and element 23 equals to 0. Again, using row 3. Before we actually do step number 6, Gaussian elimination method, we're going to have a row epsilon form. When they say row epsilon form, this is actually row epsilon form. So in the diagonal way is a 1, 1, 1, and below they're all 0, and above some numbers. Once we have this guy, that's the Gaussian elimination method. And starting from step number 6 and Gauss-Jordan elimination method. And you don't need to know the difference between the Gaussian elimination or Gauss-Jordan method, because I'm going to just ask you to do Gauss-Jordan elimination method, meaning all the way down to everything is going to be 0, just like this. 0, 0, 1, and 5. And we need to use alpha. And by looking at the first row, we have a -4. So I'm going to do R3 times 4 plus R1, put it back to R1.
0, 0, 4, 20, and then 1, 0, -4, -10. We add 1, 0, 0, 10.
For the second row is C3 over 2. So we're going to do R3 times -3 over 2, and then add to R2, put it back to R2.
0, 0, -3 over 2, -15 over 2, then R2, 0, 1, 3 over 2, 0, 1, 3 over 2, and then 9 over, and add 0, 1, 0, -6 over 2, which is -3. We have a 0, 1, 0, -3.
From here, we have x1 equals to 10, x2 equals to -3, x3 equals to 5. Determinant. In the matrix, we need to calculate the determinants. And determinants we refer to as a delta. So for the delta for any given matrix, you need to calculate very specific way. So first, we're going to talk about 2 by 2 matrix. When you have a 2 by 2 matrix, the delta is going to be AD. minus BC. The book talks about A11, A12, A21, A22, but basically this is what it is, AD minus BC. Now, if we have a 3 by 3, that's a little bit tricky part. Book gave us this example as to find the determinant of 3 by 3. You select A11 and cross this out, and the rest, you put it there. And then for the second one, A12, and then cross out, and the rest, you put it there. And 1, 3, and this guy is going to be this. Also, you need to use positive, negative, positive, this notation. And this is kind of a little confusing. I'll show you a different method, but let's do this. So find the determinant of this A matrix, delta equals, we're going to have 2, and then cross out, we have 0, 3, 5, and 3, and minus 4 and 6, 1, 3, 3, and then 7, 6, 0, 1, 5, then 2 times AD minus BC minus 4 times AD minus BC plus 7 AD minus BC, that is negative 30 minus 4 times 15 plus 7 times 30. That equals 120.
Hey, Dr. Kim, you just used the first row. Can I use the second row? How about the third row? What about the column?
Yeah, you can pick any row, any column. So for this example, we can pick third column. Based on this sign notation, we have a plus, minus, and plus, right? And 0 times the first one, 0 times something is 0. Last one, 0 times something is 0. So in this case, we need to do only once. Negative 7 times 6, 5, negative 2, 4. That is negative 7 AD minus plus BC 238. Now, let's talk about inverse matrix. We can find the inverse. Not all matrices can have the inverse. If we can find the inverse matrix of any given matrix, so let's say B is the inverse of A matrix, we multiply those two together, then it is an identity matrix, which is 1, 0, 0, 1. If it's 3 by 3, obviously we're going to have 1, 0, 0, 0, 1, 0, 0, 0, 1. And if it is 2 by 2, how you find the matrix, inverse matrix? We need to find the determinant first, which is AD minus BC, and then inverse matrix of that equals 1 over AD minus BC, which is 1 over determinant, and then we're going to change the sign, and then location is a diagonal. Let's do this. A inverse 1 over determinant of A, and that is 1 over AD minus BC, and then sign position, and that is 1 over 2. I can take this as an answer. So you don't have to multiply 1 over 2 every element. If you want to, you can. 2 by 2 matrix, fairly easy. 3 by 3 is a bit challenging. And finding the determinant, and then we need to find the C11, C12, C13. C11 is the determinant of these 4. C12 is determinant of these 4. So it's and then you need to also follow, positive, negative. So it's really complicated. I want you to learn this technique, and I want you to use this technique for our class. Finding the delta. I'm going to copy down the matrix 2, 2, 0, negative 2, 1, 1, 3, 0, 1. And copy top 2 rows 2, 2, 0, negative 2, 1, and 1. And then we're going to draw the diagonal line which contain 3 elements. So this is the first one, and we have a second one. This is the third one. Those are the only three which contain the three elements. And we multiply. 2, this is 0, this is 6. We're going to draw again diagonal line, the opposite direction, which also contain three elements. This is the first one, this is the second one, this is the third one. This time we have a negative of this multiplication, negative of this, negative of this. So negative 0, negative 0, negative, negative 4. And this will give us the delta determinant as adding all of those up. So plus 4 plus 2 plus 6, the delta is going to be 12. This is the easiest way to find the delta in the 3 by 3. You don't have to worry about the signs, right? Plus, minus, plus. Or you pick the one element and cross out and find the determinant. You don't have to worry about any of those. So we got the delta, which is determinant. To find the inverse, we need to find A transpose. So A transpose matrix. Based on this matrix A, we're going to make to column to row, row to column. So A transpose
2 to 0 into 2 to 0, row to column, and then negative 2, 1, 1, 3, 0, 1.
Then top two rows, just like what we did for the delta, copy down top two row at the bottom. And we're gonna do first two column to the right hand side.
2, negative 2, 2, 1, 0, 1, 2, negative 2, 2, 1.
And then we cross out first row, first column. Now we are ready to write A inverse 1 over delta AD minus BC. AD 1 times 1 minus BC 1 times 0. That's the first row, first column. Then first row, second column, AD minus BC. AD 0 times 0 minus BC 2 times 1. And then first row, third column is going to be AD minus BC 2 times 1 minus 0 times 1. Similar way, second row, we're going to use AD minus BC for these elements. So AD 3 minus 2 minus BC. The second one, AD 1 times 2, 2 minus 0. The third one, 0 times negative 2, 0 minus 2. And finally, third row, we're going to use this guy, AD 0 minus BC 3, AD 6 minus 0, AD 2 minus 4. So we are done. A inverse 1 over 12, 1, negative 2, 2, 5, 2, negative 2, negative 3, 6, and 6. So when do we use this inverse matrix? So just like what we did for the systems of equations, if you have a 3 by 3 equations, just like what we have before, and you find the inverse, and then inverse times the b's for this after the equal sign, that'll give the solution. So this is the step that we just went through. And also, you can find the inverse matrix using row operation. So you start with coefficients, just like a 8.2. And then instead of putting the b's in here, you're gonna just put identity matrix. In this case, because we have a 3 equations, the identity matrix has to be 3 by 3. And then doing the row operation, row epsilon form, go through Gauss-Jordan elimination, you end up getting the identity matrix on the left-hand side. And then whatever we have on the right-hand side is going to be the inverse matrix. So the Gauss-Jordan elimination technique. So first thing we want to do is writing 1, 0, negative 1, 0, negative 2, 1, 2, negative 1, 3, and then bar, identity matrix, and then we apply Gauss-Jordan elimination technique. We already have 1, yay, we don't have to worry about it. And also 0, which is good. I'm going to copy this down. We need to use R1 times -2 and add R3, put it back to R3. So again, always we need to use the first row, and then these two numbers should be matched up, okay? Add to R3 and put it back to R3. So R1 times -2.
-2, 0, +2, -2, 0, 0. That's the 6 elements in the first row. R3, 2, -1, 3, 0, 0, 1. And when we add 0, -1, 5, -2, 0, 1. So we have 0, -1, 5, -2, 0, 1.
So now we have first row, first column, element 1, 1 is 1, E 2, 1, E 3, 1, they all equals to 0. Now we need to make E 2, 2 to 1. So we need to divide first row 1, 0, 0. Second row, we're going to divide everywhere by -2.
0, 1, -1 over 2, 0, -1 over 2, 0.
To make these guys to 0, can do R2 times 1 plus R3, put it back to R3.
So 0, 1, -1 over 2, 0, -1 over 2, 0. And R3, 0, -1, 5, -2, 0, 1. Add 0, 0, negative, no, positive 9 over 2. And then -2, -1 over 2, 1. So 0, 0, 9 over 2, -2, -1 over 2, 1.
And we're going to multiply 2 over 9 for the third column. Then we have, so now we're going to work on element 3, 3, 2, 1. We did that, and we need to make E 2, 3, E 1, 3 equals to 0. So what we need to do, R3 times 1 over 2, and then add R2, put it back to R2.
So 0, 0, 1 over 2, -2 over 9, -1 over 18, +1 over 9, and then R2, 0, 1, -1 over 2, 0, -1 over 2, 0, at 0, 1, 0, -2 over 9, 1 over 2, 18 over 9, so it's going to be -10 over 18, and 1 over 9.
The last one is the -1, first row. So we're going to do R3 plus R1, put it back to R1.
3, 0, 0, 1, -4 over 9, -1 over 9, 2 over 9. R1, 1, 0, 0, no, 1, 0, -1, 1, 0, 0. Be 1, 0, 0. So 9 over 9, so 5 over 9, -1 over 9, 2 over 9.
Now we're done. This is the inverse matrix of this A using row operation.